So here is the part C of the problem. In this problem, the step response of a system is given to us, and we are asked to find out the transfer function of the system from the unit step response. Such type systems are very common. Most often, the way such type of step response are got to the system, people attach the data acquisition card and they excite the system by the unit step, and whatever the output they get, then using those results one can find out the transfer function of the system. This type of uh, identification is very common in complex systems. It is applied to the underdamped and overdamped systems. For this type of identification, the system should be stable. So let us see that how we can find out the transfer function of the system. Here if we look, there two peaks are given to us. So normally the time between these two peaks will be the same as the system will take the time to reach to the first peak. So to find out the peak time, in this case we can use the relationship TP is equal to maybe this one, this time is maybe T2 minus T1. Inserting those values will give us 0.0169 seconds. Now looking to this, it is easy to determine what will be the frequency of the system. So if I look, the one cycle, the cycle is the complete cycle. If I start, the initial input is this and then this one, so the complete cycle is this one. So to find out the frequency, so from here to here is the time period of the system. So if I want to write the time period of the system, then just I have to multiply the TP by 2. So the time period over here will be time period is equal to 2 TP, which is equal to 0.0338. And to find out the frequency of the system, now the natural frequency of the system, it is very straightforward. We can say that omega n is equal to 2 pi upon the time period. A simplification will give us that this is equal to pi upon the t peak, which is equal to 186.89, 185.893, which is approximately equal to 186 radian per second. Now the remaining thing is how to find out the damping factor of the system, because the second order equation need the damping factor and the natural frequency of the system. So here if I look to this system, so it seems to me like it will be approximately, this peak will be approximately equal to 1.5. If this one is the approximately 1.55, then the percent overshoot will be approximately equal to 55%. Now, using the basic equation of the percent overshoot, we know that the percent overshoot is equal to e to the power minus pi upon square root of 1 minus zeta square, and then a little bit manipulation can give us damping factor is equal to ln of percent overshoot, like the overshoot. So here I can say 0.55 square divided by pi square into plus ln of 0.55 square. After some calculations, we will get the value of zeta, or the damping factor in this case, is approximately equal to 0.1869, which is approximately equal to 0.19. Now, to write down the transfer function of the system, we can say that T of S is equal to omega n square. So omega n square we find out is 186 square upon S square plus 2 zeta omega n will be approximately equal to 69.5 S plus 186 square. This is originally omega n square divided by S square plus 2 zeta omega ns plus omega n square. So this was the question asked to us to find out the transfer function of the system using the step response of the underdamped system, and such type of problems are very common in the industry. Basically, we find out the transfer function, and based on this type of transfer function, we design the controllers for the system to get the closed loop characteristics according to the given specification. Thank you very much for watching the solution of this problem.